Welcome back to the deep dive. You've tasked us with a pretty big assignment, breaking down Chapter 4 of Fundamentals of Metallurgical Thermodynamics.
It's a big one.
It is. The goal here is to turn this into a concise, an understandable guide to material stability and feasibility. We're not just reading a textbook here. We're trying to give you the master keys to unlock the why of material science.
Indeed. And if you think about it, the previous chapters were all about accumulating definitions. We defined the system's inherent energy, U and H, and then we defined its inherent randomness, S.
Right.
Chapter 4 is where it all comes together. It's the crucial synthesis. It's where we combine the first and second laws of thermodynamics into really a single indispensable metric, free energy.
Our mission today is pretty clear then. We need to establish how we can predict the outcome of any material conversion. I mean, can a metal be refined? Can an alloy be strengthened through heat treatment? Will a phase change happen spontaneously?
All the big questions.
Exactly. And the central concept, the single metric that gives us this predictive power, especially in the chaotic, constant temperature and pressure world of industry, is the Gibbs Free Energy.
Precisely. This deep dive is going to systematically cover the mathematical architecture that underpins this predictive power. We'll hit the combined laws, the 4 criteria for equilibrium, some foundational equations like Gibbs-Helmholtz and Clausius-Clapeyron, and then
The big one, the
essential third law, which gives us the absolute starting point we need for any real-world calculation. Without these concepts, metallurgical engineering is just, it's trial and error.
Yeah.
With them, we can design processes with predictive certainty.
Okay, let's unpack this core idea, starting with the very definition of free energy. Section 4.1 defines it as an extensive property.
Meaning it depends on how much stuff you have.
Right, proportional to mass. But fundamentally, the definition we really care about is conceptual. It's the energy available for work.
And that phrase, it sounds so simple, but it's profoundly important. Not all the energy inside a system is useful. You could have a huge reservoir of heat, but if you can't use that heat to, say, drive a piston or run a current or perform chemical work, it's not free.
It's there.
It's just there. Free energy is the useful portion.
And the free energy of any substance isn't just a function of temperature and pressure. The authors really stress that it's influenced by a whole host of factors, many of which we're actively trying to control in industrial settings.
Oh, certainly. You start with the obvious ones, like mass and chemical composition. But in metallurgy, you absolutely have to consider the physical architecture, the structure of the material itself.
You mean like, is it a perfect crystal?
Exactly. Is it a perfect crystal? Does it have defects? Is it nanocrystalline? The crystal structure, the microstructure, and even the macrostructure all impact the system's ability to hold and release usable energy.
I thought it was really important that they included external influences here too. For instance, the gravitational, electric, or magnetic fields a material is in can actually contribute to its total free energy state.
Yes. If you're working with ferromagnetic steels, for example, you have to account for magnetic energy.
And what about for, say, metal powders?
Critically, for high surface area materials like fine powders used in additive manufacturing or sintering, the specific surface area becomes a major thermodynamic factor. More surface area means higher surface energy, which translates to a higher free energy state.
Which makes the material inherently less stable.
And more reactive, absolutely.
Okay, now that we know what free energy is, let's see how we build it mathematically by combining those foundational laws. We start with the conservation of energy, the first law. The change in internal energy, du, equals the heat added delta Q minus the work done by the system, delta W.
So du equals delta Q minus delta W. Then we layer on the second law, which brings in entropy. It defines how much heat is required for a reversible process. Delta Crev equals TdS.
And if we substitute that second law into the first law, assuming a reversible process, we get the combined statement. du equals TdS minus delta W. This equation is a thermodynamic powerhouse.
It is, because that delta W term there represents the maximum work a system can perform reversibly. And this includes mechanical work like pushing against a pressure, PDV plus any non-mechanical work like electrical work or surface work or chemical work. We call that delta W prime.
And this realization that the system can do 2 different kinds of work, that's what led to the invention of 2 distinct free energy functions, right? Both are trying to isolate that useful energy.
That's right. The first one, which sometimes gets a bit overlooked, is the Helmholtz Free Energy, which we denote with an A. It's defined as A equals U minus TS.
Based on internal energy.
U, exactly. So this function is most applicable when your system is held at a constant volume and temperature.
And the change, minus dA, equals the reversible maximum total work the system can do, mechanical and non-mechanical combined. So if you were designing, say, a bomb calorimeter or working on a solid-state material where volume change is tightly constrained, Helmholtz is your go-to potential function. It's the total store of work available.
But for almost everything we do in metallurgical engineering, smelting, casting, heat treating, we operate open to the atmosphere.
Meaning constant pressure.
Constant pressure, and often maintaining a fixed temperature. This is where Gibbs Free Energy, G, steps in. It's defined using enthalpy, G equals H minus TS.
And since H is U plus PV, using H basically accounts for and subtracts the mechanical work associated with volume change against the atmosphere, that P delta V work.
Right, which is why the change, minus dG, equals the maximum reversible non-mechanical work, that delta W prime.
And that difference is crucial. We're usually interested in driving chemical transformations, not, pushing a piston.
Exactly. Therefore, Gibbs Free Energy is the single most important thermodynamic function for predicting the outcome of pretty much all industrial, metallurgical, and chemical processes.
And let's not forget that TS term. It's so important, but often misunderstood. It has units of energy joules, but it represents the part of the system's energy that is forever unavailable to do useful work. It's tied up in the system's disorder. I like to think of it as the entropy tax. It's the price you have to pay to maintain or increase the randomness of the system.
It's the unusable energy. It gets dissipated as heat just to satisfy the second law. Every single process has to overcome that cost of disorder.
That sets the stage beautifully for section 4.2, where we formalize all of this. We're now looking at the math, assuming closed systems and, just for now, only mechanical work, to simplify the combined law into the four exact differentials.
Right. We're taking the concepts of U, H, A, and G and defining them purely in terms of the variables they naturally depend on. This gives us the foundation of, well, high-level thermodynamics.
So number one is du equals TdS minus PdV. Internal energy is a function of entropy and volume.
2. dH equals TdS plus VdP. Enthalpy is a function of entropy and pressure.
3. dA equals minus SdT minus PdV. Helmholtz free energy is a function of temperature and volume.
And finally 4. dG equals minus SdT plus VdP. Gibbs free energy is a function of temperature and pressure.
The significance of calling these exact differentials is more than just math. It's a physical declaration of power. Because these are state functions, the change in U, H, A, or G depends only on the initial and final states.
Not the path it took to get there.
Not the chaotic, winding path the reaction took.
And this path independence is why they're so valuable. It means we don't need to track every tiny fluctuation in a complex industrial system. We just need to know the initial temperature, pressure, and composition, and the final ones to calculate the change in free energy.
So the goal of all this mathematical setup is really to answer one fundamental question. What's the driving force that governs whether a system will change? And maybe more importantly, when does it stop changing?
Which brings us to the concept of thermodynamic potential in section 4.3.
Right.
You can think of potential as just an energy imbalance. When you have a temperature gradient, heat flows from high potential, which is hot, to low potential, which is cold.
Like water flowing downhill.
Exactly like water flowing downhill. When you have a pressure difference, volume expands from high potential to low potential. A natural process is simply the movement from a higher potential to a lower potential, seeking stability.
So equilibrium is just when the potential is equal everywhere, and there's no net driving force left.
Precisely. And those four exact differential equations we just established are powerful because they explicitly name the driving potential for four different operating conditions.
Let's quickly review them, keeping in mind that for any natural, spontaneous process, the potential has to decrease, so dx has to be less than 0.
Right. The first two rely on a condition that's actually pretty hard to achieve in practice: constant entropy. That usually means an adiabatic and reversible process.
So number one, for constant S and V, it's governed by internal energy. U equilibrium is when du equals 0, and the natural process drives du to be less than 0. This model's a perfectly insulated, rigid container.
And number two, For constant S and P, it's governed by enthalpy. H equilibrium is dH equals 0, and the natural process drives dH to be less than 0.
Okay, so those are foundational. But the next two are the real workhorses for engineers because they involve holding temperature constant, which is a lot easier to manage in a plant than holding entropy constant.
It's much, much easier. So number 3. For constant T and V, we use Helmholtz Free Energy. A, equilibrium is dA equals 0, and a natural process means dA is less than 0. This is important for solid-state material science where, structural integrity prevents volume change.
And then number 4, the gold standard, constant T and P. This is governed by Gibbs Free Energy. G. The equilibrium condition is dG equals 0, and a natural spontaneous process proceeds only if dG is less than 0.
And when we talk about feasibility in metallurgy, we almost always default to the Gibbs Free Energy criteria.
Why is that?
Well, because the vast majority of refining, alloying, casting, and heat treatment is done under constant atmospheric pressure in a controlled temperature environment, whether that's 300 Kelvin or 2000 Kelvin.
And this leads to a really powerful realization about how G fully defines the system's state. If we look back at that equation, dG equals minus STT plus VdP, we can derive the partial derivatives from it. Can you tell us why these are such amazing shortcuts?
They're truly elegant. If we hold temperature constant, the dP term goes away, and we find that the rate of change of Gibbs free energy with respect to pressure gives us the volume. The partial of G with respect to P at constant T equals V.
Okay.
Conversely, if we hold pressure constant, the ddP term disappears. The rate of change of Gibbs free energy with respect to temperature gives us the negative of entropy. The partial of G with respect to T at constant P equals minus S.
Wait, that is a huge intellectual leap. It means that if we can simply track how the Gibbs free energy of material changes when we slightly adjust its temperature and pressure, we instantly know two other fundamental properties of that material: its volume and its entropy.
Yes.
We've basically mapped the entire state of the system just by using G as our reference map.
Precisely. That's the utility of choosing G as a function of P and T. You gain full descriptive power over the system's state variables.
Moving to section 4.4, we use this understanding to analyze feasibility, whether a proposed reaction will actually happen. And this brings us back to that famous equation: delta G equals delta H minus T delta S.
And remember the physical meaning here. Delta G is the change in the energy available for work. Delta H is the total change in heat content, which is relatively easy to measure. And T delta S is the change in the energy that's wasted to disorder.
So the sign of delta G is the final authority. A reaction is feasible or spontaneous if and only if delta G is negative. That means the system has moved to a lower, more stable free energy state.
If it's positive, the reaction runs backward. If it's 0, we've hit equilibrium.
Now, before we get into that critical interplay between heat and randomness, we need a slight detour for non-ideal systems, especially gases. The change in free energy due to a pressure change is dG equals VdP. For an ideal gas, that's straightforward to integrate.
Right, you get delta G equals RT times the natural log of P2 over P1.
But the high-temperature metallurgical environments we care about, smelters, vacuum furnaces, they involve gases and vapors that are far from ideal.
Absolutely. The source material introduces fugacity, F here. Fugacity is essentially a thermodynamic correction factor. It's the effective pressure that a non-ideal gas should have to make the ideal gas equation work for it.
So you just swap out P for F.
You swap P for F. When dealing with real substances, the relation becomes dG equals RT dL and F. Without fugacity, our calculations for real high-pressure or high-temperature vapors would be highly inaccurate.
That makes perfect sense. It's like a mathematical cheat to keep using the simple ideal gas math, but we're plugging in a reality-adjusted pressure number.
Exactly. Now, let's get back to the core analysis. The interaction of delta H and delta S in that feasibility equation. This is where we see the critical role of temperature, T. The book outlines 7 cases, but we really need to understand the 4 corner cases where the signs are either perfectly cooperative or completely oppositional.
Let's start with the best possible scenario for spontaneity. Case IV. Delta H is negative, meaning it's exothermic, it releases heat, and delta S is positive, meaning randomness is increasing.
So if we plug this into delta G equals delta H minus T delta S, the delta H term is negative, and the minus T delta S term is also negative because T is positive and delta S is positive.
So you're adding 2 negative numbers.
The sum of 2 negative numbers has to be negative. This reaction is always spontaneous at any temperature. It's driven by both an internal energy release and an increase in disorder. It's the ultimate natural process. Think of combustion or oxidation.
Then we have the complete opposite, the least spontaneous scenario, case S. Delta H is positive, it's endothermic, it requires heat, and delta S is negative, meaning the system is becoming more ordered.
Here, delta G is the sum of two positive terms. A positive delta H plus a positive minus T delta S term, since delta S itself is negative.
So delta G has to be positive.
It must be positive. This reaction is never spontaneous in the forward direction, no matter the temperature. Think about trying to break water into hydrogen and oxygen without putting in electrical energy. It's not going to happen.
Okay, now for the interesting ones where temperature is the controlling factor. Case V, delta H is negative, so it's exothermic, but delta S is also negative, meaning the system becomes more ordered.
This is a struggle between energy release and increasing order. For delta G to be negative, the magnitude of the released heat, the absolute value of delta H, has to outweigh the ordering cost, T times the absolute value of delta S.
And that only happens when T is small.
It only happens when T is small. So this reaction is only spontaneous at low temperatures.
This is hugely important in materials processing. I'm thinking of something like precipitation hardening, where atoms have to arrange themselves into a finely ordered precipitate, which decreases entropy. The overall reaction might be exothermic, but if you run it too hot, that T delta S term grows, and the precipitate just dissolves because disorder is favored.
Exactly. You have to keep the temperature low enough to favor the ordering and stabilize the products.
Okay, and the final key scenario, which is probably the most common for high-temperature metallurgy, case listens. Delta H is positive, so it needs heat. But delta S is also positive, so the system becomes more random.
This is a reaction that requires energy input, but it generates disorder.
So to make delta G negative, the negative disorder term, minus T delta S, has to be larger in magnitude than the positive heat term, delta H.
And that condition is only met at high temperatures. By jacking up T, we amplify the entropy contribution, making that increase in disorder the primary driving force. This describes key industrial processes like smelting, the reduction of metal oxides, where you need high temperatures to overcome the positive delta H cost and let the increased randomness drive the reaction forward.
The detailed analysis of those four cases really shows us that feasibility isn't a simple yes or no, it's a function of temperature control.
And to wrap up this section, we have to formalize the concept of standard states. Why do we need this arbitrary convention in a field that's defined by absolutes?
Because thermodynamics is all about change, the delta. To compare the change from reaction A to reaction B, we need a universal shared starting line. That's the standard state, the condition where a material is stable at a specified temperature and 1 atmospheric pressure.
And for a pure substance in its standard state, we assign its activity, which we call A, a value of 1. Activity is a measure of the material's effective concentration, or its chemical reactivity. If a substance is impure, its activity is less than 1, representing its reduced potential compared to the pure form.
It's important to stress that the standard state changes with temperature. It's always the most stable phase at that specific temperature in 1 atmosphere. For pure iron at room temperature, it's alpha farad.
But if you heat it up, it transforms to austenite gamma Fe, and that becomes the standard state at that higher temperature, still at 1 at para.
And we see that with the superscript 0, like in G0 or H0. That's our signal that the property is measured relative to this defined baseline. It gives us the necessary reference point for all practical thermodynamic calculations.
We've established that delta G predicts feasibility and that we need a standard reference point, G0. Now the real challenge begins. Tracking how that feasibility changes in the inferno of a steel plant. Part 3 is all about the mathematical machinery that lets us track delta G across huge temperature and pressure ranges.
We start in section 4.6 with the fundamental equation for tracking these changes. The total differential d delta G equals delta VdP minus delta SdT. This compact equation shows us that the change in free energy depends only on changes in volume, pressure, entropy, and temperature.
Let's first tackle the dependence of delta G on temperature. In an industrial context, we often need delta G for a reaction that spans hundreds or thousands of Kelvin. We can't just assume delta H and delta S are constant across that range.
Right, they change too.
They change too. So the source material details the complex calculation of the standard free energy change at some temperature T, which we call delta G naught T. This is a multi-step integration process. You start with the known standard enthalpy and entropy at 298 K, and then you integrate to account for the thermal changes.
And this whole calculation hinges on Kirchhoff's law, which requires integrating the difference in specific heats between the products and reactants delta C naught across the entire temperature range.
In simple terms, delta Cp naught is defined by these polynomials that vary with T. You have to integrate those polynomial expressions from 298 K all the way up to your operating temperature T to accurately find the final enthalpy and entropy. It accounts for the energy needed to heat the reactants versus the products.
So that simple equation, delta G equals delta H minus T delta S, is only ever really accurate if you're working very close to the reference temperature.
Or if you can assume the change in specific heat is zero.
But in high-temp metallurgy, that assumption can introduce massive errors.
Huge errors. Now, moving to the pressure dependence, section 4.6.2 looks at how delta G shifts with pressure. Since d delta G equals delta VdP at constant T, we just integrate from a reference pressure, usually 1 at T, to the actual pressure P.
So delta G at pressure P equals delta G at the reference pressure plus the integral of delta VdP. The key piece of information you need here is delta V, the change in volume during the reaction. For reactions involving only solids and liquids, delta V is often tiny.
It's negligible, meaning pressure has very little impact on delta G. But if you're dealing with a reaction that involves a gas phase, like reducing iron ore in a blast furnace or synthesizing compounds at extremely high pressures, the volume change is significant, and that pressure integral becomes a dominating factor. You have to know the volume change precisely.
Putting the temperature and pressure dependence together gets you to the general expression in equation 4.62, which is the full, complex roadmap for calculating delta G under any non-standard condition. It's the ultimate statement of delta G's dependence on state variables.
Okay, let's transition now to section 4.7 and the powerful Gibbs-Helmholtz equations. This seems like another way to track delta G with temperature, but why is it so essential?
It's the bridge between feasibility and measurement. The goal of Gibbs-Helmholtz is to determine delta G as a function of temperature using only calorimetric data, specifically the heat change delta H.
Which is relatively easy to measure.
It's easy to measure delta H with a calorimeter. Delta G, however, requires knowing entropy, which is much harder to determine directly. So Gibbs-Helmholtz turns the difficult measurement into an easy one. The derivation is, it's really elegant. It starts with the definition G and that partial derivative we already found. At constant P, dGGT equals minus S.
We substitute that minus S into the definition G equals H minus TS, and with a bit of algebraic manipulation involving the quotient rule, we arrive at the core relationship. The partial of G over T with respect to 1 over T at constant P equals H.
And for a chemical reaction, it's even more useful.
Yes. The partial of delta G over T with respect to 1 over T at constant P equals delta H. This tells any engineer, if you plot the ratio of delta G over T against the inverse of temperature, 1 over T, the slope of that curve at any point will immediately give you the enthalpy change, delta H, for the reaction at that specific temperature.
So in other words, if you measure the temperature dependence of feasibility, you get fundamental information about the heat of the reaction without having to run a separate calorimetric experiment.
It's one of the most essential working equations in chemical thermodynamics, and we should mention its counterpart, the Helmholtz equivalent, which relates the change in A over T to the internal energy, UU. But for our purposes, we stick to the Gibbs form.
Okay, moving to section 4.8, we hit Maxwell's relations. These feel like a thermodynamic hack, a way to find difficult variables using easy ones. Where do they come from?
They're purely a consequence of the fact that U, H, A, and G are exact differentials. Since the change only depends on the start and end points, the order in which you take the derivatives doesn't matter.
So the mixed second derivatives have to be equal.
They have to be equal. Applying this principle to those 4 fundamental differential equations gives us 4 concise relationships. For example, from the dG equation, we get the relation that the partial of S with respect to P at constant T equals the negative of the partial of V with respect to T at constant P.
And the significance of that is huge.
Immense, because entropy, S, is hard to measure directly. But volume, V, pressure, P, and temperature, T, are all easily measurable in the lab. Maxwell's relations let us calculate how entropy changes with pressure, the term on the left, by simply measuring how volume changes with temperature, the term on the right.
It's a fundamental bridge between the measurable world of PVT and the abstract world of S.
Let's look at some of the critical applications derived from these relations. Starting with internal energy, U. We can use a Maxwell relation to derive a key relationship for how internal energy changes with volume at constant temperature.
Which is the partial of U with respect to V at constant T equals T times the partial of P with respect to T at constant V minus P.
Now, why go through that pain? Because if we test this on an ideal gas where PV equals RT, that complex right-hand side simplifies perfectly to 0.
It proves it.
It mathematically proves from the foundational laws of thermodynamics that the internal energy of an ideal gas does not depend on its volume when temperature is held constant. It's a powerful validation of our simple models.
And we see a similar proof for enthalpy.
Yes, using the Maxwell relation from H, we find that the partial of H with respect to P at constant T is also 0 for an ideal gas. So the enthalpy of an ideal gas is independent of pressure at constant temperature. These relations tie everything together.
Okay, the most intricate, but maybe the most practically important application here is the derivation of the relationship between the two heat capacities, Cp and Cv.
Right. This is a deep dive into the system's ability to store heat. The difference, Cp minus Cv, is the extra energy you need to heat something at constant pressure because some energy is spent doing mechanical work, that P delta V work. The textbook derivation uses multiple Maxwell relations and culminates in the general expression. Cp minus Cv equals V times T times alpha squared over beta.
Okay, let's unpack those new terms. Alpha is the isobaric coefficient of volumetric thermal expansion, how much the material expands when you heat it.
And beta is the isothermal compressibility, how much it shrinks when you apply pressure at a constant temperature.
And this relationship is highly instructive for solids. For metals, the difference between Cp and Cv is small, but it's not zero. The equation stresses that to fully describe the thermodynamics of a solid metal and accurately calculate its potential changes, you have to experimentally measure its thermal expansion and its compressibility.
You can't ignore the volume effects in high-precision metallurgy.
Finally, in this part, section 4.9 introduces the Clausius-Clapeyron equation. This equation is indispensable for predicting or controlling phase transitions.
It is absolutely vital for managing things like the boiling point of metals under vacuum or how pressure might affect the melting point of a casting alloy. The derivation relies on the fundamental equilibrium condition. During a phase transition, say from phase 1 to phase 2, the Gibbs free energy of both phases must be equal. G1 equals G2.
So if you change the temperature and pressure a tiny bit, the new equilibrium state requires dG1 to equal dG2.
And since dG equals minus SDT plus VdP, you set the differentials equal, rearrange, and you get the fundamental form. dP by dt at equilibrium equals delta S of transition over delta V of transition, which is also equal to delta H of transition over T transition times delta V of transition.
This equation basically defines the slope of the phase boundary on a pressure-temperature diagram.
Right. Delta H is the heat of transformation, T is the transition temp, and delta V is the volume change.
Now, when you apply this to melting or solid-solid transformations, like the shifting allotropes of iron, the source material notes that because the volume change, delta V, is extremely small, the slope dP dt is very large.
Which means you need a massive change in pressure to just slightly shift the melting point?
The solved problems confirm this. Increasing pressure by 100 atmospheres might only change the melting point of lead by a fraction of a degree.
In normal metallurgical operations, pressure has a negligible impact on condensed state transition temperatures.
However, the most practical form of this is for vaporization or sublimation, where a liquid or solid turns into a gas. Here, the approximations are significant and valid.
First, we assume the volume of the resulting vapor is huge compared to the volume of the original liquid or solid, so delta V is approximately just V vapor. Second, we assume the vapor behaves as an ideal gas, so V vapor equals RT over P.
You make those substitutions, integrate, and assume the heat of vaporization is constant over a short range, and you get the integrated form, equation 4.100. The natural log of P2 over P1 equals negative delta HVAP over R times 1 over T2 minus 1 over T1.
This equation is critical for vacuum metallurgy. It quantifies the exponential increase of vapor pressure with temperature. Since delta H of vaporization is always positive, the higher the temperature, the faster the metal evaporates. Clausius-Clapeyron lets us calculate how deep a vacuum we need to prevent excessive material loss during high-temperature processing.
All right, before we get to the final fundamental law, let's quickly cover two helpful shortcuts engineers use for quick estimates. These are empirical rules based on observation, but they're surprisingly accurate. Section 4.1 Burrow covers Richard's rule.
Richard's rule is about fusion, or melting. When researchers plotted the heat of fusion against the melting temperature for different metals, they saw a pattern. The entropy change upon melting, delta SM, which is delta SM over Tm, is roughly constant. It falls in the range of about 8 to 17 joules per Kelvin mole.
So if you know the melting point of a metal, you can quickly estimate the heat needed to melt it. It's a good first guess when you don't have precise data.
Similarly, section 4.11 covers Trouton's rule for vaporization. This rule states that the entropy of vaporization, delta SVAP, is approximately constant for many substances boiling at 1 atmosphere, with a value commonly cited as 87.864 joules per Kelvin mole.
This one is even more robust than Richard's rule. If you know the normal boiling point of a metal, you can get a really accurate estimate of its heat of vaporization. These empirical rules just underscore the inherent similarity in how materials transition between phases.
Now we move to the final, indispensable piece of this chapter, the third law of thermodynamics in section 4.12. And this isn't just theoretical, it's what makes all our calculations in the previous parts practically possible.
Right, we keep calculating changes, delta H, delta S, delta G. We established that when we integrate to find entropy, we always end up with an integration constant, S0, the entropy at absolute zero. The first and second laws don't define this S0. We need an absolute reference point.
That need was first addressed by Nernst's Heat Theorem back in 1906. Nernst observed, by looking at plots of delta G versus T and delta H versus T, that as temperature approaches absolute zero, the two curves merge. Their slopes both approach zero.
And since we know the slope of the delta G curve is minus delta S, and the slope of the delta H curve is delta Cp.
Nernst concluded that for reactions involving substances in the condensed state, the change in entropy, delta S, and the change in specific heat, delta Cp, both approach zero as T goes to 0 Kelvin. All processes at absolute zero occur without a change in entropy.
This was then generalized by Max Planck's refinement, which became the modern third law.
Which states, the entropy S of any pure and homogeneous substance in the condensed state in complete internal equilibrium may be taken as zero at T equals 0 Kelvin, S0 equals 0.
Let's linger on that condition, complete internal equilibrium. Statistically, entropy is a measure of the number of ways the atoms can be arranged in a system. S equals K times the natural log of W. For entropy S to be 0, W, the number of possible arrangements, has to be 1.
Meaning the material must be in a single, perfectly ordered lowest energy state. A perfect crystal.
The source material is very careful to note that real metallurgical systems often deviate from this. If you cool an alloy too quickly, or it freezes into a solution instead of a pure crystal, you can freeze in some randomness.
Which leads to a non-zero residual entropy at 0 Kelvin. But for the purpose of engineering calculations involving pure, stable crystalline forms, the assumption that S0 equals 0 is universally adopted.
And the consequences of this definition are profound. It provides the foundation for absolute calculation.
The first consequence, derived using Maxwell's relations, is that the thermal coefficients of volumetric expansion, alpha, and pressure, eta, must both approach zero as T approaches 0 Kelvin. Basically, materials stop changing their fundamental physical properties as they reach absolute zero.
The second and most critical consequence for us is the ability to calculate absolute entropy. Since we define S0 equals 0 at T equals 0, we now have the lower limit for our integration. St equals the integral from 0 to T of Cp over T dt.
This means we can now use measured specific heat data, Cp, to calculate the true absolute entropy of a material at any temperature T.
And this absolute entropy value is what feeds back into the Gibbs Free Energy calculation.
Right. The third consequence is that the third law allows us to calculate the change in free energy at any temperature using calorimetric data, starting from delta H0, the enthalpy change at 0 Kelvin.
And finally, at 0 Kelvin, since S is 0, our definitions simplify completely. G0 equals H0 and A0 equals U0. The third law anchors the entire thermodynamic system to a definable starting point, allowing engineers to move beyond relative changes and into absolute quantitative prediction.
That was a comprehensive deep dive into the mathematical and physical core of material feasibility.
We started with the foundational concepts and ended with the necessary 0 point. Let's try to consolidate the core concepts.
I think the key takeaway from this chapter is that Gibbs Free Energy, G, is the ultimate dictator of material behavior in the constant TP environment that we work in. If delta G is negative, the reaction is driven to happen spontaneously.
We tracked the evolution of this metric, seeing how the combined laws define the four thermodynamic potentials, U, H, A, and G, and how that critical feasibility equation, delta G equals delta H minus T delta S, shows that temperature is often the decisive factor.
Especially in processes that trade a heat requirement, delta H, against the creation of disorder, T delta S.
We acquired the tools to deal with non-ideal systems, like fugacity, track G across wide temperatures with Gibbs-Helmholtz, and map phase boundaries with Clausius-Clapeyron.
And critically, we realized that Maxwell's relations provide a means to measure difficult variables like entropy, using only easily measured P, V, and T.
And finally, the third law provides the absolute reference point for all entropy calculations, confirming that thermodynamics is not just a study of change, but a system of absolute state definition.
If you leave with 3 key insights, let them be these. First, the sign of delta G is the ultimate engineering check for feasibility. Second, controlling the feasibility of high-temperature reactions is almost always about manipulating T to make sure the magnitude of that minus T delta S term dominates the enthalpy change.
And third, quantitative predictive metallurgy is impossible without defining two things: the arbitrary but essential standard state reference.
And the absolute zero reference provided by the third law of thermodynamics.
The source material referenced how converting graphite to diamond at room temperature requires over 14,000 atmospheres of pressure just to overcome the slightly positive delta G. So given that extreme pressure needed for an unnatural transformation, I want you to consider a modern materials challenge. Synthesizing highly complex intermetallic alloys or manufacturing bulk metallic glasses often involves rapid controlled cooling. What cutting-edge materials process relies entirely on running a process just above or below the critical transition temperature to precisely manipulate that delicate T delta S balance, favoring an otherwise unnatural structure without requiring immense pressure.
An excellent thought experiment to illustrate the power of T delta S control. Thank you for trusting us with your deep dive into the fundamentals of material stability and feasibility.
We'll see you next time.